Welcome to Wireless Future. I'm Emil Björnsson and I'm here today with Eric Larsson. How are you?
Good morning, Emil. Good, how are you?
Good morning, I'm great. And this is episode number 40, so we have been going on in this podcast for quite a while.
40, wow, that's amazing. I mean, 40 is like a birthday, right? So when did we actually start this project?
I think it was in the autumn of 2020.
Yeah, it was in 2020 during the COVID, in fact. Yeah,
exactly.
So we aren't at the 4-year birthday yet, but we'll be approaching it. But we are at the 40th episode. Let's say celebration. That's right. Yeah.
Right. And in this episode, I was thinking we will look back at something that we talked about earlier, but not that far back, because 2 episodes ago you were mentioning about synchronization in wireless networks, and you were promising, we should talk about this in an episode in the future. So let's do that today.
Yeah, synchronization. Sure.
Right.
To start with, that's a very broad topic, and it's a fairly complicated topic, and above all it's I think fair to say more complicated than what it might seem at the surface. And it's also a topic that isn't dealt with so well in a lot of modern books on comm theory and maybe MIMO particularly, right? Because very often in like digital comms textbooks and first courses that we teach, and especially the MIMO comm theory books and literature, we usually start off with a signal, something of a sort like received signal is equal to transmitted signal plus noise, right? And this could be continuous time, something like x of t equal to s of t plus noise. Sometimes there is a linear filter in there, so x of t is an impulse response convolved with the signal plus noise. Typically we sample the model, so we work in discrete time, so something like x sub n equal to and then convolution of an impulse response with the s sub n plus noise. But now in reality, to start with, whatever we call a signal in all these models, that always represents some physical quantity. Something of the sort like a voltage that's measured somewhere, or a voltage that's fed to or like used to control a voltage generator or something of that sort. And there are lots of effects here that will need to be properly modeled. I mean, to start with, communication channels are, well, to a good degree, they are linear time invariant, right, within the coherence time of the channel. But there will be all sorts of things going on, like non-linearities in electronics. There'll be quantization that's non-linear and so on. But it'll also be the fact that for these models to even be well defined, the transmitter side and the receiver side will need a common notion of what time means. So if I'm X and you're Y, or whatever S we said, and I say X of T and you say S of T. Okay, so does T have the same meaning for you and me, right? Are we talking about like the signal with respect to the same time reference? And that's one aspect of synchronization.
Yeah.
And another aspect is that typically we have models that are obtained by demodulating or representing complex baseband, something that goes on at a narrowband carrier. And then we also need an agreement on what the carrier frequency is. So synchronization, I mean, most broadly speaking, is like about getting agreement on these things, right? What does time mean? What does frequency mean? And so on.
Right. And I think this is an important point that you're bringing up, that when we write textbooks and make courses, we focus on the thing that someone thinks is the essential things to really understand communication performance, what is the limits on performance that you can achieve. And then when we say a channel, we always think about the channel between the transmit and receive antenna when the wave propagates over the air, but it actually also includes the transmitter hardware and receiver hardware, and then there's all kinds of hardware effects that we don't usually model in textbooks, and synchronization is certainly one of the important aspects there. I remember when we had some project course that the students had learned everything in our previous courses except the synchronization question. So then my first question for you is really, so why do we need synchronization? Can't we just transmit the signal and then the receiver does it best to just untangle what we sent.
I mean, again, it comes down to the model that we alluded to here making sense, right? So that we can actually say that received x of t is your s of t plus noise, whatever. And broadly speaking, there are a few different kinds of synchronization. So number one, we need at least a course time synchronization. If we think of like a modern system with OFDM, then transmitter and receiver will have to be synchronized in time within the cyclic prefix of the OFDM symbol, so that any mismatch in timing just comes across as some additional excess delay of the channel, or can be absorbed in the impulse response and fits within the excess delay of the channel.
Right.
So that's the number one thing, and that's kind of an easy thing because cyclic prefix is long in comparison. And the second aspect is frequency synchronization. So we have to agree on a carrier frequency. My oscillator or clock has to tick at the same rate as yours, so that when I say 1 gigahertz, then you when I tune to 1 gigahertz, you also tune to 1 gigahertz. And if there is a mismatch here, that will turn into a leakage between subcarriers in the OFDM system, in an OFDM system. And that is, well, that's not an easy problem, but it's a manageable problem. And typically the way this is done and has been done, I mean, for generations of systems, is that there's a signal, a synchronization signal broadcast by the system or by the base stations. One synchronization signal to get the course time sync and another one to get the course frequency sync. And everybody listens to this and does something of the sort like, well, maximum likelihood estimation or whatever to get timing and to get frequency sync. So these are the two main things.
Right.
And then there is the third, which is synchronization in phase, which is sometimes required. And then we should keep in mind here that for a narrowband signal, phase and time are essentially the same thing, right? Because we have a narrowband signal and we time delay it by, say, delta. That is if delta is small enough, that's equivalent to phase shifting the signal by 2 pi fc delta. Fc is the carrier. So in a way, time and phase synchronization are the same thing. But when I say course time synchronization, that happens at a much, much larger time scale when we talk about synchronizing phase. So when we talk about being synchronized in phase, then we're talking about delays less than a wavelength, phase rotations much less than, I mean, just a small part of the unit circle. And in terms of time, we're down to tens of picoseconds, obviously depending on the carrier, but that's the order of magnitude that we're discussing.
Right.
So those are the three things: course time, frequency sync, and sometimes phase sync, or phase alignment is another term that's being used. Yeah. And sometimes phase calibration, depending on the exact context where we care about the phase.
And I believe in this kind of scenario, time and frequency, these are two constants from a sort of theoretical point of view. It's not like we consider that someone moves close to the speed of light, so there is any time dilations or anything like that. So it's more that like in the hardware components, we just don't know the time and frequency, the exact one, if there is such a thing, but there is some mismatch between the transmitter and the receiver.
That's right. I mean, there's no relativistic effect here, right? I mean, nobody moves that fast. So that's true. And then, well, constant, I mean, oscillators or clocks that drive the electronics, they will drift over time. So even though we have like even though the carrier frequency between transmitter and receiver differs at some point, then we estimate the difference and adjust for that, they will continue to drift, and this difference will have to be like re-estimated from time to time. But that's a manageable problem in general. So
I remember you talked about things being narrowband. If I understand it correctly, it's sort of you have a certain carrier frequency. You have a signal that oscillates back up and down like a sinusoid, and then some of the properties there is what you use to carry information. You might be slowly varying the amplitude at a much slower phase, which is sort of slower time delay. So it's sort of many oscillations before you change the amplitude, or you might have some shifts where you carry information here as well. So if you just change the amplitude, do you need to have phase information at the receiver as well? I mean, if you do some kind of amplitude shift keying or something like that.
So let's break this down. So we're talking about communicating with a narrowband signal here, right? And demodulating coherently. So if you want to demodulate phase coherently, then you'll need the receiver to have an estimate of the carrier phase. And the typical way of accomplishing that is to first send a pilot and measure the phase of the pilot, and then you use the phase of the pilot to, adjust your. This is done in software, typically. I mean, algorithmically. So that's entirely true. For coherent demodulation, you need to estimate the phase of the carrier.
Right. Yes. So I think in some of the basic digital communication textbooks, when you consider different modulation schemes, you have sort of amplitude and phase, or I and Q parts, and you put out different points in the constellation diagram there. I guess if you have a course time and frequency synchronization but not phase, then this constellation diagram at the receiver side will be rotated somehow, and
that is entirely true.
Yeah, and if those rotations causes issues, if you are using the phase to carry information, this is a big problem. If it's only amplitude you're using, it might be less of a problem.
That's entirely true. I mean, so again, let's break this down and talk about a point-to-point link where we send information-bearing signals using a carrier-modulated or narrowband signal with constellation points representing the I and Q of that narrowband signal. Then you'll see, in the presence of a phase misalignment, or if the receiver has not been able to estimate the carrier phase properly, that will show up as a rotation of your constellation diagram. So it will just appear like rotated. So rather than like in the textbooks, it will be just rotated by some angle. Yeah. And if there is a carrier frequency offset, that angle of rotation of your constellation diagram in turn will rotate over time.
Right. Yes, and I think sometimes this is maybe as deep as textbooks are mentioning some of these issues, because there is, for example, the discussion about differential modulation schemes where you send a first signal, so you don't assume that exactly you know the rotations from the beginning, right. But you send a signal in the beginning, and then you code information into how you move around in your constellation diagram for the rest of them.
Right, and that might be a good point to make, in fact, that differential modulation, I guess differential PSK is the standard thing that you can find in textbooks. Demodulation of differential PSK is essentially equivalent to sending a pilot or a reference signal or a demodulation reference signal, I think is the term, and then using that pilot to estimate the carrier phase and then demodulating the rest of the symbols coherently. So essentially you're just estimating how the constellation diagram is rotated.
Right. So I guess that is a principle we could use then. If I have a mobile phone that connects to a base station, my phone sends a pilot, and then it sends a sequence of data, and that's the uplink transmission. But if we then want to transmit back in the downlink, what can we do?
So now this is going to get a little more technical here. I think we should break this down by first understanding the uplink properly. So let's say that, again, like in your setup here, that there's a mobile that transmits a narrowband signal, and then we are receiving that signal through a receiving antenna. If that mobile just sends a pilot signal or a pilot symbol and then data symbols, all complex baseband, then the receiving antenna can estimate the phase of the received pilot, and that way get the phase of the carrier and use that to rotate or compensate all the data symbols that follow subsequently. And that way get estimates of constellation points that lie properly in the complex plane, so without the rotation. And now in the uplink with multiple antennas, and these might be in a single array, they might be distributed, whatever, doesn't quite matter. So in the uplink, then the mobile is sending the pilot. Every antenna does the same thing. Estimates the complex angle, or the amplitude as well, but phase is really what's important here, mainly. So every antenna does the same, estimates the complex amplitude, or especially the phase of the channel or the carrier phase, and uses that to rotate the received data symbols. And once that rotation has been performed, or derotation rather, then those symbol estimates per antenna can just be coherently combined, just be summed up. Yeah. And this requires nothing in terms of synchronization or calibration among the antennas, because all the data symbols undergo exactly the same propagation, the same phase rotation as the data symbols. And if the clocks in the antennas are off relative to each other, this doesn't matter. They don't have to agree on a common phase reference or anything. There's no need for any synchronization or calibration among the antennas here. They could be driven by the same oscillator, by different oscillators, it doesn't matter. Of course, at some point, you'll need to send pilots frequently enough. If the oscillators drift over time, or if they are slightly off in frequency so that these phases rotate over time. But there's no need for any sort of calibration or anything here among the antennas. So that's the uplink. Now, you asked about the downlink.
Yes, exactly. So now you have this multiple antennas at the base station, and you said, okay, we use the same pilots. You don't need to send multiple pilots, and you derotate the things, and then it's essentially like a textbook example with all of the different.
Yes. So the uplink is easy. Now the downlink is considerably more complicated. So in the downlink, what we want to do then with multiple antennas, and right now, let's make no assumptions on whether these antennas are co-located in an array or distributed or whatever, but we want them to cooperate phase coherently, such that they can all can send the same, let's say, QAM symbol to the mobile, and we want our transmissions to add up constructively at the mobile.
Right.
Now, for this to function, these antennas will have to be jointly synchronized or calibrated in phase in some way. And the exact form of calibration that is required depends on the operation mode. But one way to understand the fundamental need for such synchronization or calibration is just to consider that, suppose that we know propagation exactly. So we live in a world where we know that there is a mobile and we have two transmitting antennas. And these two transmitting antennas are 1 meter away from the mobile each. Suppose we know this. And suppose that we just want to send a direct impulse to the mobile. And we want to send this impulse in such a way that it's received simultaneously from both antennas. Now, for this to be possible at all, these two antennas will need to agree on when to perform that transmission. And so they will have to be synchronized in time. This is not how to start. We don't transmit impulses, obviously, but typically the way that real transmission works in MIMO and TDD MIMO in particular is by using reciprocity. So by estimating the channel from an uplink pilot, receiving that pilot at each antenna, forming the complex conjugate of that pilot or of the channel estimate that it gives us. And then pre-rotating the transmitted signal by that complex conjugate. This is called conjugate beamforming or maximum ratio beamforming. And it turns out for that to work, these antennas will have to be calibrated or synchronized in phase relative to each other. Particularly, they will have to be reciprocity calibrated relative to each other. That is not exactly the same thing as them agreeing on like a global time reference. And explaining the difference, I think, goes slightly beyond what I could do here without using like math, and it's hard in a podcast show to do. But I think we can. But it's important to appreciate the point and the fact that for joint coherent beamforming and downlink to work, the antennas that participate in the downlink transmission, when we use reciprocity-based beamforming, will have to be synchronized to each other in phase or calibrated, specifically reciprocity calibrated. Sometimes this is, if they are distributed in space, the antennas, then we say jointly reciprocity calibrated very often. And another term that's being used here is aligned in phase. So these are basically also synonyms.
So let's see if I understand this properly. So in the uplink, you send this pilot and the data, and I guess in principle you can send the pilot last as well, because you just store the received signals.
You could send the pilot to come anytime, assuming that the phases don't drift over time. So let's say the oscillators are totally stable over time, just generate perfect sinusoids, but they are off by some unknown phase relative to each other.
Right.
Then on uplink, your transmission has to contain a pilot. Actually, I'm not sure that's strictly true. There might be like algorithms you could decode blindly and so on, but let's not go there. But sending a single pilot is enough.
Yeah.
And the important thing is there is no need for any calibration or reciprocity calibration or synchronization or anything between the antennas and uplink. Just go ahead with the transmission. Yeah.
And my point there was sort of that you take the information from this pilot, and then in your computing you are doing this derotation, and then you add up the signal from different antennas. So you can do this afterwards. While in the downlink, right, it's really important that you do it first before the transmission occurs, in order for the signal to add up over there instead of in the computer.
That's right. That's another good point. I mean, on downlink, there's also the causality requirement here, that we need to know the channel state information before the transmission so we can pre-rotate. But in the context of understanding synchronization and calibration and alignment, then it's really the fact that it's not enough to get the pilot. These antennas actually have to agree on a phase reference relative to each other, right, for the joint transmission to even to work. Yeah.
And if you have sent this pilot in the uplink, you get some kind of phase information about what you should derotate. Isn't it enough to just use this information and then send with the opposite phases in the downlink? Or it seemed like there's something more here, right?
No, or there is something more, yes. I mean, this is exactly the core of it, that for downlink, it's not enough to just receive the uplink pilot and then compute the complex conjugate. You need this alignment between the antennas. They have to be jointly calibrated for reciprocity, or synchronized for reciprocity, or aligned for reciprocity, whatever. There are a couple of different terms here that all mean the same thing. I tend to say calibration, even though calibration to a lot of people implies that you tune a small pot with a screwdriver, but it's not really what's going on here, right? This is more like actually estimating things. So maybe synchronization is a better word, I'm not sure.
Right. So how do we do this then? If you have an array at the base station with many antennas, how can we accomplish this kind of synchronization?
Yeah.
Is there some basic principle?
Yeah. So this is a tricky topic. Okay. But let's see if we can break this down. So let's talk about first a co-located array of antennas. And there's a lot of stuff going on in an array to start with. There are antennas, right? There's electronics and all sorts of stuff. And if these antennas are closely located to each other, there'll be mutual coupling that will affect things back and forth. Now, and there's lots of misconceptions floating around as well about all these things, and let's not go there in today's discussion, but stay with the fact that mutual coupling, to start with, is a linear and time invariant effect. There are a few things here. There's this load pull phenomenon, for example, where the gain of an amplifier can be affected. But when you speak to hardware designers, they'll tell you that this only happens for poorly designed hardware and poorly designed arrays. So in principle, this coupling is a linear time invariant effect. And then when we speak of a channel, when we speak of propagation, then we know about reciprocity holds. Yeah, reciprocity of propagation always holds in physics. But then when we speak of a channel, then we need to define, what does the channel mean? When is the x of t in your model? What does this mean? So typically that's a voltage somewhere you define over something you can measure, right, in your circuitry. And depending on exactly how we define what air quotes the channel means, then there might be effects that need to be compensated for here because of coupling, okay? But bottom line is that these are linear time invariant systems. So in principle, propagation is reciprocal between elements within the array and between antennas in the array and a mobile somewhere else. So why would we need any reciprocity calibration here then, or care about this matter at all? Well, for two reasons. So first, within the array, even though propagation itself is reciprocal because of the linearity and time invariance, there will be electronics chains that aren't, okay? There'll be analog filters, there'll be mixers, there'll be other components. And these components, their characteristics and the phase lag of the signal when it travels through these components will be slightly temperature dependent. I think there might be some weak dependence, like when these components age over time, that they change in their characteristics as well. But the main effect here is that temperature affects the phase lag. And that in turn creates a non-ideality that varies over time and needs to be compensated for. Yeah, typically called reciprocity calibration in the array literature. There is also everything I've said here now so far assumes that systems are time invariant, yeah? And that implies particularly that all antennas in this array are driven by the same local oscillator. So that oscillator might drift over time. But if it drifts, its phase drift and its phase noise will affect all elements in the array in the same way.
Right.
Okay, so...
Is that a good thing or a bad thing?
What do you mean? That the oscillator drifts can never be a good thing, but the fact that it affects...
fact that it affects all of them in the same way, maybe we don't need to compensate for something.
Let's not go there.
Okay.
Okay. But anyways, bottom line here is that propagation is reciprocal, yeah. But certain components of the hardware chains, mixers and filters and amplifiers, aren't. So there is a phase lag that varies slowly over time, and they will need to be estimated and compensated for. And this is all now true for a co-located array driven by a single local oscillator.
Right.
And calibrating away these reciprocity errors that come from differences in phase lag in the analog electronics chains, that is typically done by measurements between antennas within the array. Yeah? So basically like having one antenna transmit and the others listen, having another antenna transmit and having the others listen, and so forth. And then solving a regression problem essentially to get per antenna an amplitude and phase for the uplink and another amplitude and phase for the downlink. And from these estimated phases, getting coefficients that can be used to compensate the array such that it appears reciprocal when beamforming to a mobile terminal. Right. So that's the essence here. These methods that rely on transmission between antennas in an array, they've been around for quite some time and they are well tested in practice. I don't know what goes into the main, like in the product lines of 5G equipment, but I'd think that something of this sort is bound to be there at some point. I mean, there are other ways of accomplishing the same thing, but that requires extra hardware components and a lot more complicated stuff.
Right.
I think it also might be worth pointing out that in some literature, this transmission between antennas in the array is called to exploit the mutual coupling, which is not totally accurate in terminology, but I guess it's we can still say like that, but it's not totally accurate. Mutual coupling has a very specific meaning in electromagnetics. So what's really exploited by this method is propagation from one antenna to another within the array.
Right. I guess this is what they call S parameters when people are working more with antennas. One of the way of explaining this is also that the models that we are using in the complex baseband, this are sort of describing what happens at the transmitter and the receiver, but not including all the electronics there, because we are generating a radio frequency signal in the transmitter, and then it flows through all this component you were saying, go over the air, goes through some other electronics at the receiver, and then it's sampled and goes to the complex baseband. And the fact that these components are different between the antennas and different depending on which direction you are having the transmission, these are the kind of things that you are dealing with.
That's right. I mean, one more time, for conjugate beamforming or maximum ratio beamforming to work on downlink, then every antenna estimates the channel and uses that channel estimate, takes the complex conjugate and uses that as a beamforming coefficient on downlink, right? But that assumes that these antennas are reciprocity calibrated relative to each other. And within a compact or a co-located array, that's well tested how to do that by performing these measurements between the antennas. And again, I mean, explaining all the details of that would go, I think, beyond what we can accomplish in a podcast show here, but it's done in many papers, obviously. Yeah.
But one last question regarding that aspect. So when you have sent these signals around between antennas to figure out the mismatches and you want to compensate here, this compensation is done in the digital baseband, or do you start to touch the hardware components as well?
Oh no, I mean, there would be no reason to touch the hardware components, since all the beamforming anyway is done in software, right? I mean, we're talking about like multiplying with complex numbers, and in like a massive MIMO system, the beamforming is also multi-user, so there would be like superposition of different streams and all sorts of things going on. So that would be done in the digital domain completely. I think another point to be made here that could be good to know for the audience is that when performing this antenna measurements within the array to perform the reciprocity calibration, then propagation between antennas within the array is exploited. But there's no need here to make any assumptions on what that propagation channel looks like. So there's no need to know like how large is the phase lag when I transmit from one antenna to the next, the phase lag within the array. That's an unknown that can easily be eliminated from the equations, and all what remains in the end is this phase lag that we have in the electronics, in the amplifier and mixer and whatever analog filter chain that depends on temperature. So that's the one that's being solved for here.
Right. So, and when you have done all of this reciprocity calibration that you described, suppose I now would like to send a signal in the 30-degree angle out from my base station antenna array. Do I know everything I need to know in order to do this now?
No. So that's a good question. Look, I mean, what I said here about reciprocity-based beamforming and reciprocity calibration within an array, that goes for reciprocity-based beamforming and nothing else. Yeah. So there's measuring among the antennas within the array and solving for these unknown phase lags in the electronics hardware chains. That's perfectly possible. It can be done without any prior information about what the array looks like, how the propagation between antenna elements is like, or anything. Yeah. But the result of running such an algorithm is only useful for reciprocity-based beamforming. This only functions if the mobile sends a pilot, and this pilot is received and complex conjugated and all of that. It's not useful if you want to use the array for beamforming into a particular physical direction, so like your 30 degrees. So it's not useful if you want to do like fingerprinting for localization or anything of that sort. And you need a different type of calibration, which is not as easy to accomplish. So that's a different thing. I don't know if we should go there because it gets incredibly difficult to explain these technical points without really drawing on the whiteboard. But point is well taken here on the fact that if you want to calibrate your array so that it can resolve and really map received or transmitted signals to physical angles, then number one, we need to know something about the geometry of the array, obviously. And number two, we need a different type of calibration as compared to the reciprocity calibration. Yeah.
Right, yeah. So the mapping between all of the channel parameters that we get in order to deliver data strongly at a certain locations based on pilots, and the mapping to geometrical parameters like angles and these type of things, this is much more complicated. And I think this is also very important, even if we don't go into the details on how to achieve such calibration, that you need an even deeper calibration if you should use all of the signal processing methods that relies on sort of looking at channels, extracting angles, having there's compressed sensing methods that looks at the received signal and try to figure out what angles were there in the multipath environment. So this might be much harder to achieve in practice.
Indeed.
All right, so suppose you leave this co-located array case where, that means all the antennas are essentially at the same physical location in some way here. And you start to spread out the antennas more and more, and would like to build a distributed array. Maybe it surrounds me here in the room, or maybe there are more spread out than that. Can you still synchronize these things?
You can, and I think for the discussion we should stick to joint reciprocity calibration. So the target here is now that we have a mobile and they'll sense a pilot, and pilot is received that is different antennas, and it's complex conjugated and then is used for beamforming. Then so the signal should add up coherently, right? And so the key thing here is that there is no difference in principle between reciprocity calibrating a co-located array of antennas or co-located distributed antennas, or small panels or whatever, or distributed arrays, let's say. Joint reciprocity calibration among the elements can be accomplished using exactly the same technique, namely by pairwise bidirectional measurements between pairs of antennas. And this can be done without knowing the propagation distances. So we can put up an antenna here, another antenna over there. We don't need to know the distance or anything between them. We can still calibrate them jointly for reciprocity by bidirectional measurement between them. So the difference or the distinction between the co-located case and the distributed case is that typically, in the co-located case, typically we have a single local oscillator that drives all the circuitry, right? So the source of reciprocity errors here is really only that because of temperature mainly. The phase lag in the transmit and receive branches very slowly over time, and it's quite stable over many hours. If the equipment is cold, you turn it on and it heats up, then the phase will drift, quite significantly. You'll have to calibrate. But once it's warm, it kind of stays constant over a very long time. But in a distributed system, you might not have the same oscillator. You could have. So that's a design question. You build a distributed MIMO system. How are you going to distribute clock and phase? Will you have like a central oscillator somewhere and then some expensive cables that distribute the phase reference? Or will these antenna access points or antennas, will they have their own little local oscillator? If they have their own little local oscillator, then these oscillators, their phase will drift apart over time rather quickly. And once that phase is drifted apart by maybe more than, if you need more than, if you're in the wrong half plane, then the beamforming won't work at all, right? So you'll probably want to be within 10, 20 degrees or something, or for null forming, you want to be much more tighter, within a few degrees even. So every time the phase of these local oscillators is drifted apart by more than some threshold value, you'll need to recalibrate for reciprocity, for joint reciprocity, in order for reciprocity-based downlink beamforming to work. So therein lies the key difference. Not how you actually perform the calibration. It's the same technique over the air by measurements in between the antennas, but how often you have to do it.
Right. So then that becomes more of a practical challenge, perhaps, if you need to do it much more often. It
becomes a practical challenge because if you want to build distributed antennas or MIMO systems, then you could opt maybe for a solution where you have a central clock that generates, could be a lower frequency, but it would have to be extremely stable, and then that would be used to align the local clocks at the antenna so they don't drift relative to each other over phase. But this requires requires expensive hardware and cables, and my vision is rather that no, if we're ever to really gonna build distributed MIMO on any larger scale, then these antenna panels or access points or just distributed antennas, they would have their own local oscillators. And for a local oscillator, it all comes down to cost, basically, how stable its phase is over time. Yeah, I mean, if you put up like $1 million, you can get something that goes into a GPS satellite or is atomic clocks that basically keep the phase for a year, maybe a very long time, right? But if these are gonna cost like 10 cents a piece, then their phase might be off by, you might be halfway around the unit circle in a few milliseconds. I mean, so. Wow. Yeah, and then you need to recalibrate very, very often to maintain the joint reciprocity. So there's this trade-off here. How good are the oscillators versus how often you would need to realign the phase?
Right, and I think both you and me have been working on this kind of distributed or cell-free massive MIMO scenarios in the hope of deploying a lot of antennas in a distributed fashion and maybe emphasize particularly what performance improvement that could have in the communication parts. But do you think synchronization in such a scenario will be so expensive that you can't build this at the reasonable price?
No, let's not speculate about cost. Quite don't feel qualified to do that because it's just it all depends on how the market evolves and all of that, right? So I would, but if I had to bet on something, I would say no. But I think quite generally, one would want to keep the cost down, which means in this case not having relying on expensive installations, deployments of cables for the purpose of synchronizing phase, but rather rely on over-the-air measurements between antennas. And then the question is, okay, so how often can we afford to perform such over-the-air calibration measurements? And that will determine how stable the oscillators have to be, and in turn how much they will cost, right? So I think we probably should approach the question from the other angle, that from a COM theoretic point of view, how often could we afford recalibration? This is not such an easy, many of these problems, they seem like at the surface, this is something somebody will solve in the lab, right? So we don't care. But actually, some of these problems they're super important, and they have a lot more intellectual depth than it seems at the surface, and they're quite challenging to solve. And I think there is there's quite a bit of research problems here that simply will need to be addressed, right? For example, if you think of it in a TDD system, then we have a TDD timeline, so we do uplink and then downlink and then uplink and then downlink. But now if we have antennas or access points that suddenly need to talk to each other in order to align their phase or calibrate themselves to each other for reciprocity, then one of them will have to transmit while the other listens. So we'll have to break the TDD pattern here, which will have implications in terms of, okay, but suppose that here's an access point that was actually engaged in serving a user somewhere in TDD beamforming. And now somebody tells us that, hey, you need to recalibrate your phase and start talking not to that mobile, but start talking to another access point over there. Then who's going to take care of the mobile? I mean, and if there are latency constraints, this is not such an easy thing to solve, I think. So if you want good research problems, then here's a topic that what seems to me rather few people actually have thought so carefully about and maybe are even aware of, and where there's good potential actually to do many good things.
Yeah, definitely. And as you were saying, the important thing is that we will have a limited amount of resources to do this kind of synchronization in real systems. So we need to do the best we can under those circumstances. And I would guess that if we go up in frequency and use higher frequency bands, then you also in general needs to send pilots more often to learn channels, and then you also are more short on resources somehow.
Right. So almost everything I know becomes more difficult when you go up in frequency. So that is true. I mean, mentioning here like research problems. There is also, of course, a potential to develop advanced tracking algorithms. Figure out how often do you need to perform this recalibration, and maybe if you have in a heterogeneous deployment, you might have some antennas or access points that are maybe locked in phase or better locked, or have better quality oscillators, and some that are cheaper and will need to be more often attended to. And I can imagine a lot of totally new research problems here.
I think some of the mechanism that you have been describing now about how you send signal back and forth, if I understood correctly, sort of, it's particularly the discussion is based on how do you provide the system with the observation that you need in order to sort of untangle the synchronization issues. But then even if you have enough observations, there will always be some estimation errors left in your the equations.
There'll be noise, there'll be interference, there'll be non-idealities.
Right. So between every pair of antennas, there will be some kind of synchronization errors. If you now do this over a big system, will these errors sort of accumulate and break down somehow?
Yeah,
or?
That's a very good question. So the question is really, if you now perform calibration measurements with the purpose of jointly reciprocity calibrating the antennas, you perform measurements between pairs of antennas, right? And then the question is, according to what topology should you actually perform these measurements? And if you have a large network, then could it happen that in one part of the network you're kind of locally calibrated, but in somewhere further away you're locally calibrated also, but then in between of these parts there'll be large errors, because errors accumulate as you like keep hopping around between nodes in the topology. Yes, the short answer is yes, that this can definitely happen, in fact. It's not such an obvious thing to analyze, no.
Right. But there is some aspect of divide and conquer here, I guess, as well, or a hierarchicalness that different parts of the network can synchronize themselves at the same time, maybe not interfering much with each other, and then you can build up the synchrony between different parts of your network as well.
Yeah, I guess in practice you probably would want some sort of algorithms like that, but it actually turns out to be optimal to solve a single joint reciprocity calibration problem for the entire network, and then use the result everywhere to compensate the phase when you perform your beamforming. That's a basic result that can be proven.
Right.
Then in practice there might be other reasons that you want distributed algorithms, obviously, but yeah, these are intriguing questions. Yeah.
Yeah, I guess when we say optimal in the estimation theory area, in terms of then estimation performance, not necessarily.
Actually, in terms of beamforming accuracy in the end.
Yeah, but the complexity could of course be huge with the optimal schemes in these cases, so that can be a reason.
That's right. Complexity doesn't scale well when you make the network larger and larger. No.
Right. So now we have covered this topic from many different angles, and hopefully not lost too many listeners along the way. But for those who have been staying, what else? Is there anything else to tell?
I think there is. I mean, look, you say we covered the topic. I think it's more accurate to say that we scratched the surface of the topic and mentioned a few aspects of it. So, however, I don't really feel that it is possible to go in much more depth in a podcast conversation like this. More than that, I hope that we've been able to make listeners aware of this sort of issues and perhaps inspire some to take a look at the papers that we have in the field and think about the open questions and the open problems that are there.
Right. So then we will add some papers in the description of this episode in case you would like to have more of a technical detail on this topic.
Oh, yeah, absolutely. Let's do that. Yeah.
All right. Thank you very much for your enlightening explanations of this topic.
Well, thank you, Emil. Yeah, and then so also to the audience. So remember that we are on YouTube, of course. We also on Apple and Spotify and Google. So the audio track of our conversations can be downloaded, and you can subscribe on Spotify and on Apple and Google and what else did I say? Spotify.
I think those are all of the places.
That's right. Those are the places, yeah.
All right. So subscribe so you don't miss our next episode. And thank you very much for listening. Bye-bye.